Thank you, Professor. Thank you for the introduction. Also happy to be with you guys here. And also said I can actually present one of our unique projects here with you guys, which is a good example, which exactly is a good example as the title is also written, data-driven design for the entire life cycle, which I think we managed to show and illustrate. And yeah, let's start, I would say, without spending too much time. Maybe before I head to the project, I will say a few words of myself. I'm also a former student of Professor Hall, which actually he just joined when I did my master thesis presentation. So since then, I'm always happy to be here in this class and taking part also in his lectures with guest lecture that I can do. My name is Gianluca Genova. I am I'm managing the Digital Innovation Laboratory in Basler Hofmann. This is a laboratory which I will also introduce in a following slide. And also I have some of my colleagues today with me as well joining, which are also former alumni from ETH, and it's always a pleasure to be back. In the meantime, besides my job in Basler Hofmann, I also take a lot of initiatives in Building Smart. I am the Building Room Steering Committee member in International, and also taking some voluntary activities also in the National Building Smart in Switzerland. I've studied in ETH, my master's in integrated building system. Initially was a trained architect, and since then I am in Basler Hofmann taking action with all the digital transformation relevant activities and developments. So in today's agenda, in this short presentation, I will give a quick overview of our team, of our company, a bit about our project, which I will use as a case to illustrate the data-driven design over the life cycle. I will tell a bit about the project goals. I will give some insights of the three main designs or three main phases like design, construction, operation, and I will conclude my presentation, which giving some statements about the benefits of fully digital approach. So a bit of about my company. Basler Hofmann is a Swiss engineering and consulting company, which you may be already familiar with. It has approximately 800 employees, consisting of different disciplines, mainly engineers, construction engineers, civil engineers, energy engineers, specialists, architects, and so on. We have projects in Switzerland and as well as international locations. We have main headquarters in Zurich, but we are mostly distributed in Switzerland, in German-speaking part like Lausanne, like Basel and Bern, but also we have in the French-speaking part like Lausanne or locations. And also in international, we have in Germany, in Slovakia, in Singapore our offices. What we are doing is we are developing pioneer solution in construction, mobility, energy, and safety, and we are really interdisciplinary established, and it's a very own family company since 1963. And what is always a pleasure to also present and show our companies here also is because we're always looking for smart trainees like you guys. So that's why you're always welcome to join and get in contact with me later on. A bit of about our team that I'm working on together. I'm working together is IDALab, which I'm managing. It's in the German expression is Integrated Digital Together Work Laboratory. It's called Integrated Digital Arbeiten Labor. And what we are doing is we're providing solutions towards digitalization or company, if it's consulting or it's about building, establishing the model, is about even extending the usage of BIM before BIM and beyond BIM, all this innovation approach around it. And we also establish certain services in digital areas, whatever it's to do with new technologies like VR or AR or simulations, or as well as really latest technologies like recapturing or software or platform development. Everything which can be done with BIM models is kind of our area or interest area. What is special about my team, a few words, which also you will see in the whole presentation, which is always I will repeat, is we are interdisciplinary team. We have different backgrounds, which I think it's a really essential thing that once you want to do digital approaches or you want to develop digital solution for the project, you need the insights from different backgrounds. And then another added value is the fact that we are really international established. It's not about the languages that we speak, but it's also the cultural different thinking that brings together a value also to tackle the different challenges in the digital world. What we are really used to is we are really integrated together. We work in a collaborative way. We approach the problem as a whole team problem. And usually what makes the difference is that we have this digital mindset or digital talent, if you want to call it, or sensibility, that we are trying to really tackle the problems, not as the shortest way, but the smartest way, which wherever we can use the digital solutions or data-driven approaches, there we want to try to implement it. Okay, a bit yet about a project which I'm going to talk is an extension project in Esslingen, which is our own extension project in a building in Esslingen. What is special about this location is these 3 buildings belongs to Basler Hofmann itself, and whenever we have this kind of tradition that whenever we build a project for ourselves, we just don't do it in a seek of building a building and providing office spaces, but we are trying to also do it in a way that we can learn something from it new. So in the A building, traditionally, if we go back in time and we look at the A building, you will see that it was the first energy certified office building in Switzerland. In B, you will see this plug and work building system and HVAC concept that was introduced first time. C building is one of the Energy P Eco building, office building in Zurich Canton, which is unique, and it's also pioneer in using different energy, renewable energy sources and technologies. And then when it comes to the question, okay, the A building, now we have to do the extension, we really took this radical decision by saying, okay, it's the time to digitalize, it's the time to do it through the latest stage which is possible in the state of art, and we said we are going to build this building with a BIM methodology, and we are going to build this building without drawings. And that was our first challenge that we did with this project. So the project is not complex as itself. I mean, it's really simple, an extension building. It contains a cafeteria, an extension of the Mensa, the canteen. It has some additional 12 offices on the top, so it's nothing special about it. But what is special was it's an early adopter BIM pilot in Switzerland, and it was the first project which was fully constructed through a model without using any drawings. And that was, I think, or printed drawings, let's put it this way, to be more consistent. And that's the project where we were lucky, I would say, to win the small project award and from Autodesk in IAC Excel Awards 2 years ago. And also we were nominated for the innovation category in ORG Awards 2 years ago as well for this project. So what is special about this project is every participant who is involved in this project design was from beginning on in this single one model. Everyone was working together. Even though the architecture company was not Basler Hofmann, still we managed to integrate it in the model by repeating his work and establish it in the same model together with him. And at the same time, by forcing everything in one model, we created a single source of truth, kind of by making sure that the model is the center of the project. And because it was our own building, from the beginning on, it was clear that we wanted to use it for the entire life cycle, because once it's completed, we knew that we are going to live with that building. We will keep the model, and we can use this as a digital showcase for ourselves to encourage the employees in the company, but as well as for the clients to show what is possible if you really go in a fully digital approach. And we wanted to build it without printed plans, not because we wanted to save papers and do something nice for the environment, because we wanted to change the mindset by taking away from the people the most conventional tool that they have, the paper and drawing. So by forcing them to think in the information model. So to think about the model, to think about the processes. If someday we wouldn't have any plans anymore, any drawings anymore, what would you do? To answer this question, we forced them actually to do this. And that was the driver decision here by deciding to not use plans. And also we wanted to try as much as we can new technologies and construction methods in this building. I already said the motivation of the printed drawings, but of course, this conventional 2D plans that we could neglect it in the way that we designed, but we couldn't avoid it for certain processes for certain processes that we couldn't change because of some legal reasons, because of cultural reasons, so on. So we did have the plans, just we didn't use them, we didn't create them, we didn't print them, and internally we didn't use it. But for a good example, for the permit, for example, to get the permit from the canton, we had to print the plans because they had to stamp it somewhere. So in the end of the day, we had to still print the plans, but we forced it as much as we could, and surprisingly, actually, we managed to build the building without printing the plans end of the day. But of course, we had this 2D view still in the project. So what I always say here, there's nothing so useless as doing efficiently that which should not be done at all. And that's the thing, like we should not focus how we can create faster this 2D illustration of the model, because the model itself is more smart. And so that's why that was our also driven idea here, to not focus on the details and the things that we shouldn't do at all. Instead of that, think differently. And we starting from design phase, it was clear that a good BIM model, which has to go over the life cycle, has to be in a good quality. So we have to have really an approach to build intelligent model. Now I will give an example of the MEP design, because that's what my team is located with, and that's what we are more familiar with. So I will give all the design examples in MEP, but then in the construction stage, I will be more generic and so on. So in MEP design, there are some aspects which made a model-based approach or data-driven model really intelligent. And what we see is kind of a key thing that has to be implemented in a model. First thing, we have to use the advantage of real-time model coordination. I will explain a bit what I mean with that. We believe that a product-oriented design is essential because you want to know what you are going to build, and you want to make sure that such a product exists. System logic embodied, that seems to be a logical thing, but I can assure you that most of the model in the market doesn't have this logic embodied in the system, in the models. And calculation simulation from the model is like a natural thing that you would think a BIM model should be able to do, but again, you have to have consistent data, you have to have really consistent data structure, and also your algorithms and simulations should work together simultaneously to actually realize such simulation calculations. And interdisciplinary coordination is a key always, because you as an MEP designer should know how to work with architect and structural engineer. And you have to, a good example I will give from the provision for voids and provisions that you have to do in the walls. That's a really good example for it. And model-based tendering was a big key. And doing the assembly from the model is also something really challenging that I think should be considered an intelligent model. So the real-time coordination, I mean, maybe you heard about clash detections, like everyone tries to avoid clashes in the model, and everyone would say the best benefit from BIM is you can do clash detection. Well, I would say, yeah, that's true, you can do it, but I think that's not the integrated approach that we are looking for. I'm more interested to actually do clash avoidance instead of clash detection, because everyone is synchronized and integrated together. Why would you even create the clash in the first place if your technology allows you to see what the other are doing? And that's, I think, the approach what we want to try to implement. And since then, that's the way that we work in our company. So we do the clash detection just for quality assurance and not as a base or standard process. Then, if you are familiar with Revit, I mean, you know that it's something, or any BIM author tool, you will know that you will have this kind of work separation, that every element belongs to someone. So there's a kind of this boundary definitions that everyone can own an element and can close it and block it. Well, that's it's a good thing. That's actually how we managed to build work all together in one model. But that requires a lot of discipline, a lot of respect to each other, a lot of communication that people are not used to before. And that was a big change management that we learned through this. And always when we model something, we have always a culture, like we always go from the consumer to the source, meaning, so if you know the endpoint where you want to go, you go first, you place that and you model from that back. So on the way back, you can then see other people. As closer you get to the technical room, you will see that actually the coordination is more efficient. And that's kind of things that we establish. And more communication is necessary. It's like, you can imagine like this, like modeling all together in one model is like moving in the construction site all together. Everyone should be aware of everyone's movement. You should know who is where, and yeah, that requires a lot of communication, which is a good thing, which we didn't do in previous times too much, or not enough. Product-oriented design is, I think, the second thing from intelligent model. So some people will still say, well, you can also do it with generic families or with generic objects. It's okay. They just have to look similar, but they don't have to be that one. True, but actually the thing doesn't just end with the geometries itself. It has a lot of information which is really product specific that also kind of influence your internal processes in the model project. And the actuality of this data, it's something that we as a construction engineering company cannot follow. So it's impossible that we can know all the products in the market and all the data and so on. So that's why we don't want to take any liability issue with that. And then functionality is something that is really important for the calculation simulations. And I told you that it's really important that there's a consistent structure in everything. That's why you cannot just use the product as itself in the model, or the product element as itself in the model. But of course, there are some databases or libraries in between will make sure that everything is in a certain structure. But what is important, that this functionality of these components are kind of ensured that actually we can do some calculations with these elements and that the data are correct. And then another thing is, maybe every pump look the same. That's why you can say we can use a generic placeholder for that. But then there are some special things in every product that the installation points are really different. So that's why if you want to make it really sure that this model is an assembly model in the end, you have to be aware that every element that you model, that you use in the project, should have a certain reality in the backend. And that is something that we cannot avoid if you always use a product-oriented, if you do a product-oriented design and you know which products are going to use, you get also free consulting from this producer because they are happy that you choose them. And that's something that would be a waste if you don't use this potential of this ecosystem. System logic embodied is really simple. It's the difference that something looks geometrically correct and something is data, in terms of data technology, correct. So every component should belong to a system. It's not just in a thing in the building system, it's also in the structural engineering the same, in architecture the same. Everyone has its own system, and you have to build this kind of data layers to the elements for many reasons. I mean, these are things to ensure that you didn't forget anything. This kind of things ensure that you don't forget anything, and also it makes you potential. It also helps you to make the calculation possible, to also helps you to handle the model in a meaningful way. Because if I give you a model like this, as you see in the picture, it looks colorful, it's nice, but then after the day, if you give it to a specialist, they cannot do much with that if the subsystems and all the systems are not embodied in the model. Calculation simulation, I will not go into too detail since you are not HVAC engineers, but what is important here, that the model is used for a supply and demand comparison, that actually you are providing, the model is providing the design, the capabilities, the engineering that the client is requiring. And this kind of things can be ensured through this kind of calculations and this kind of comparison. You can quickly ensure that every room is heated accordingly, every room has enough light, every room has enough water, and so on and so on. And you can do this kind of comparison really fast in a model-driven or in a structured model, I would say. Yeah. Interdisciplinary coordination is a coordination when you have more than one disciplines involved in certain things. A good example is a hole that you do in the wall. Like a simple hole that you make in the wall requires a lot of coordination. I mean, it's not just a structural engineering thing. It starts from the MEP designer will request a hole in the wall, then the structural engineer has to prove if it's the hole still affecting the static or not. Then the hole has to be closed. Then again, the fire protection guy ensures that this hole is not affecting any security or any other fire issue or any code. And this kind of things can be done with emails, can be done with PDFs here and there, or you can really do a smooth data-driven approach by actually using the model to do this kind of checking through a software or through a solution, that a workflow that you develop. And that's what we did actually here. We use a software which helps you to automate it, coordinate all this inputs from different disciplines, and when everyone approved, the hole was opened. So this kind of thing. And if something was rejected, there was coming a suggestion, and this kind of process. I mean, usually such a process would take a week in a conventional way. In this project, it took us like maximum a day. And this kind of things are the added value of working in an integrated model. So I think this is the part where most of the companies are questioning, okay, when you build such a model, how we can do the tendering? Because most of the companies, which are installation companies or stakeholder contractors, they are not used to see models. They are used to evaluate drawings, and if they don't get their drawings, which are used to, they will have hard times to actually give a price to it. And I mean, we were actually not sure in this project when we started, even if there would be, if we would get any bid for any contractor, because we knew that people would get scared, and we knew that everyone would not jump and take the risk to do it first time. So what we decided, okay, let's keep it simple. Let's decide some good partners that we think they can see this as a chance too, and they can collaborate with us. And we give them the model. Really simple. We give the model and told them, okay, give a price to this model. We didn't prepare any scheduling. Maybe did prepare some schedules, but we didn't prepare any paperwork or any drawings to them to help. We told them exactly what we are seeing in the model. We want them to be built. So how much does it cost? And that was not the ideal approach, of course, but at that time being, we didn't have anything. We didn't have to establish any workflow to handle the tendering. And interestingly, actually, it worked out fine. I mean, also when the building was completed, we didn't have any issues, and actually the stakeholders, actually they were happy that they didn't have to do all the paperwork as well, and they could really early think about the details, discuss with us about solution, optimize the model, and that was the added values to have a tendering model based in the first place. Then when the tendering was completed, then it's not like that every model can be built. Like, you cannot take every BIM model and go to the construction site without any negotiation with the installator company to make it, in a way, an assembly model. Like I said, any building information model is not a building assembly model in the same time. So a good example to understand the difference is, I always give this duct example in this project. Imagine that a designer say, I want a 10-meter duct. So for them, in terms of engineering, hatchback engineering, that's just okay. I mean, it's the air flows 10 meters straight through a floor. But in terms of an assembly installator company, there are certain things, certain parameters that has to be considered. First is, these ducts are produced from a machine. So this machine cannot produce every length. So every machine has different length maximization. In this case, our producer was saying a duct can be maximum 1.85 meters. So this is kind of the limitation that it was given. So it's a kind of a parameter that we should know when we build a model. Secondly, you have to consider the accessibility, the logistic. So there are a lot of things which influence kind of assembly model. And then where the cut has to be done because of statical reason, because other things. And all of these things, a normal designer company would not know this in details, because they never had to deal with this kind of things, because it was in the early time really easy. You give it the drawings, they deal with it, they do their assembly drawings themselves, and we didn't have to know anything about it. Like, since until this project was done, none of my hatchback engineers would know what is the longest production duct in Switzerland, in Zurich. They didn't know. I mean, they didn't had to know, but it was interesting. And that with this information, we actually adjusted the model and segmented everything accordingly. And the same we did with pipes, with ducts, with every cable trace, or with other components which has to be segmented. Yeah, that was a good learning, and that's the difference between assembly model and building model, building information model. And then we went to the construction side. And building from a model or the model-based construction requires different methods. I will just briefly will give some examples how we can build a building from a model. When you have a BIM model and you have it segmented and you make it as detailed as an assembly model, after that, the production is something that you can actually also do data-driven. So I will go back to this ventilation example. So if you have the segmentation there and you know every duct size, actually what you can do is you can extract this data and you can feed it directly to a CNC machine to produce this duct. And we have two advantages here. One is you can actually control every product which is produced has an equivalent in the model. Secondly, you can, in this process, hide an information within this code so that actually when it comes to the site again, you can recognize it back which part of that was in the model. So that's what was our advantage. So we hid a Revit ID in the production code so that actually when this ducts was produced, the producer didn't know what that code means, but for us was a big link again back to the model. So they just stick the papers on the duct and they send it to the site. And then what something cool happened that actually we could actually manage with this the logistic. We could manage with this. We could know exactly which duct has to be mounted, installed in which part of the building, and that was a big help. And another thing is it's about the staging. Like if I would give you the model that I showed you before and then say build it, you don't know where to start with the model. And this is something that we call it. I mean, staging is not new. It's totally something that you would do also in the drawing with the drawings. But in the model, it requires also certain preparation before, because so that actually when you're in the site, you can exactly view what you need to view that you see, so that actually you don't see the whole model at once always. You can just see the information that you require for that part of the installation. So I like always this word, like if someone gives you the elephant, how you're gonna eat it, you will say one bite at a time, and that's exactly what you do with the model. You cannot build it everything at once. You have to go step by step, and the installator guy will ask you every day, okay, what do I have to do today? Is it possible that I see only the things that's relevant to today? And that's exactly what you have to establish in the model way beforehand, so that actually they can handle this in the construction side. So there are certain model-based assembly methods that we use in this project. One is the visualization model view. So it's like using a model viewer directly visually. It's not different than drawing. Just instead of seeing 2D drawings, you see 3D models. It's still the same, but it's just cooler. And the second part is the method. It's the point-to-point method. It's really simple. You take a point in the model. It shows you in reality which point is that. Object-to-object method is really similar to the point-to-point method. Instead of taking the point, you take the object as a whole and it's illustrating to the side. And digital fabrication is like you don't need the human being at all. You let the robots do everything themselves, and that's actually where you just rely that if they print or they use accordingly. So it's more like they use object-to-object method and point-to-point method combined, but doesn't matter. The robot's gonna do it anyway. So the model viewer version is really simple. Like I said, you have this certain staging views that you need to view, and then based on this view, you can measure it from the tablet or whatever, and you can build it accordingly on the site. There is no really added value compared to drawing. Instead of you just see it more better, you can see the coordination better, you can see the relation better in 3 dimension, but the information which is delivered is not different that much. So nothing disruptive here, except instead of using a paper, you use a drawing. It's still better than drawing. We don't need to prepare these drawings for each effort, but for the installator guy, it doesn't change that much. So the second method, which was point-to-point layout, is actually really cool thing. You can select certain strategical points in the model, which you think it's important. Structural engineers love it. So that's the best thing what they use. I mean, point by point, they built the whole building. So they use for each column, for each wall, and a corner from the component. And the guy with a pen place the points one by one. I mean, for structural engineering, it's great, but also for installator companies, for example, for electric engineers, which has hundreds of components in one room, was a big help, because you could just place this machine in the middle. You could just select any point, and it will tell you exactly what the switch are, where the light is, where they have to make a hole, and all these things. So without using any meter, they just finish a room in half time they would use it in conventional way. So these are the added values, and the accuracy is really high. I mean, of course, human being can make mistake everywhere, but I can assure you in the construction site happens more mistakes. So that's why actually get a bit help from a machine which is a laser accuracy, it's always better. I'm not saying that the people will not do mistakes again, but still less than before, for sure. And now the third object-to-object method. If you remember back the Duct example and the production that we did with the Duct, we managed to stick a paper on each Duct when they were delivered to the site. So the only thing that you need now is some device. It can be a HoloLens, a fancy AR solution, or it can be a simple mobile app, doesn't matter, which scans this code and tells you which object it is and where it belongs to. I mean, you can use this for simple logistical problems. But if you want to make it more cooler, you can use this AR and scan the Duct, and the AR tells you where to place the Duct, and even check if it's placed correctly. So that's actually what we try to develop here. It was more an innovation thing that to make something fancy, but actually, if you just take a part of this technology or method, you can optimize a lot of process in the construction site. So we developed an app, of course. We had to, because that was possible at that time. But actually, the installator guys just use it in a larger room where it's safe to move, because if you ever use this kind of glasses, I mean, they are cool, but they can ensure that you don't hit something where you're walking, or it's not really construction safe. So that's why you cannot use it in a really dangerous construction site like that without someone observing you. So actually, there is no saving if someone has to observe the guy using the AR, and the other guy has to use the AR, and two guys have to place the Duct. So you need 4 people to do a simple job that before maybe 2 people were doing. So it's nothing optimized here. But in the future, I think once the AR are more safer, installation guys can use them themselves, I think then you can optimize a lot of processes. Right. So another object-to-object method, I mean, it doesn't have to be a Duct, it can be also a wooden piece, is this acoustic wall that you see now in this picture. It's a research project, actually. It's part of our cafeteria decoration, but it's also an ETH research project together with Gramazio Color Research and the Digital Fabrication Lab, together with Anne Holzbau, which is our industry partner in this project, actually built this acoustic wall. What is special about this wall is, or this acoustic installation is, it's firstly produced by a parametric design, of course. Everyone knows Dynamo Grasshopper, so that's nothing special about it. But what is special is, there are 2 special things on this project, maybe. One which I found special is this object inertial tracking. That's the fancier expression of my object-to-object method expression, but it's the same, actually, not different than the Duct. It was for each wooden piece, it will tell you if it's placed accordingly to the model or not. But what is more interesting is that the shape that you see here, it's not just nice looking shape because it's decorative or aesthetic. It's because the design was informed through a result of acoustic simulation. So actually, we did different measurement tests in this room, and we took the negativity of the simulation results to reduce the noise at maximum with just a unique shape, right? And that's always nice because it's kind of physically informed. It has a physical meaning behind it, and usually kind of forms that are defined by the nature are usually the most beautiful and aesthetic ones. So that's why you don't need to create yourself a parametric definition. You can rely on a certain natural physics or scientific fundaments, and then you suddenly get a really unique shape, which is also cool and functional, and yeah, it's also probably efficient. So you can see the simulation here. That was the input to the parametric tool, and on the right side you see the AR. This time is not a glass, it's a camera, but principally the same. Is check if objects are in the right position. If not, it's red. If it's green, it's cool. And yeah, so basically that's how it works. And you don't need any drawing here to build this wall. Actually, I don't even know if you can build it with drawing, but yeah, that's, I think, the cool part. The next digital fabrication example is the future tree. It's you see the wall, it's in the cafeteria, and just outside this cafeteria and the men's, there's this fancy wall tree, we call it. It's a combination of parametric design and robotic prefabrication. There are two different technologies you can see here. One is the column that you see from the tree is 3D printed. It's called with eggshells, also together with ETH, a collaboration. It was a collaboration project. For also it's a color research, ETH, the Digital Fabrication and Robotic System Lab, and Erne Holzbaut again for this construction. And this time, what was the shape giver? One was the statical simulation, and another was the natural limits of the material. So this too was the driver of this design and this shape. So when we say data-driven design, is not just data that we produce, there are also scientific data that also can inform a design. So what is special about this is the 3D printing part. So actually we didn't print the concrete, we just print the shell. So that's why it's actually the shell is printed here. And the shape of this shell is unique about the durability of this metal. It's a plastic polycarbon component, which I think with several tries, I mean, if you are in the ETH, you see down the labs, I think someone from the lab can explain you more in detail. But what is unique is here, if you see the shape is really like it doesn't have too long cutting. It's always have this unique diamond shape, and this is because it's with minimum material to keep the maximum pressure of the concrete, so that actually this shape is actually made. It's the reason of this material properties, and that's define the shape. And actually, it's also aesthetic, but it's more cool when you know the scientific reason behind it. And then the steel was a prefabricated steel piece, was installed inside, and it was cured. And then it's called eggshell because you can then peel the polycarbon framework out of the concrete wall column. And the robotic with assembly arms is the same. We have this parametric model with all this nails pre-parameterized. I mean, you could play with the geometry and it will adjust itself. It's a statical model that was behind it. And once you have this model, the robot arm will just install it based on this 3D model, this upper part of this roof tree. It's exactly the same technology which is used in the ArcLab in ETH. If you would see in the roof, if you will look at, it's exactly the same company, the same robot, and it's the same technology. But the only difference is it's like a self-standing tree. It's just a different form. All right, what was the experience with the model-based assembly? I mean, everything starts with the coordination with the contractors, installation companies, whoever you want to call it. It has to be as early as possible because their input influenced the design of the model. The acceptance of the construction site, surprising, was really good, but the change process should not be underestimated. The assembly work preparation was done from the model way before you came to the site. So actually they could solve most of the construction site problems without even starting the construction site, which was great. And the supplier, not the installator companies, but the supplier and producer, if you go in the whole ecosystem, if you go one step even further, their input is even way more important to get an accurate model. Like remember the example of the duct installator. If the producer wouldn't tell us the machine capabilities, we wouldn't even install it or prepare the model in the same way. And staging, predefined model view is like the key from model-based assembly in the BIM world. Like I call it micro MVDs. In the Building Smart, we call it model view definition. In Revit, it will be in view or whatever. It's just a partial piece of the model with certain geometries and information. That's what I understand here. It's really crucial. And in order to build a fully building, you cannot just go with one technology. You have to use multiple technologies and you have to use it in the right place where make it sense. So you cannot just say we build it the whole with the points, we build it all with AR glass. You need a combination of both, because not always everything makes sense everywhere. And okay, you get rid of paper, you get rid of a lot of things, and you say, okay, we are fully digital. But then you have to also understand that the ICT infrastructure requires also certain things, like a Wi-Fi connection in the basement means if you don't have it, the construction site stops. Like, you know, they're crazy things. So we did this construction site in the summer. At that time, we had this latest iPad Pros. We used those. And no one expected that actually this iPad Pros, if you put it under sun for more than 3 hours, they will just shut down. They will overheat it. I mean, we had to stop the construction site 3 hours because of Apple. Like, you know, this kind of things. Or Autodesk used the BIM 360 platform. They decided suddenly to play with the language settings. The whole BIM 360 was Chinese for a day. Yeah, I mean, things like that. I mean, data-driven approaches, model-based construction, everything is great, but you have to also be careful that everything is also, the mistakes can get really fast to everywhere. So you can make really important changes with one click. And that's why, yeah, it requires other disciplines then. Right, operation phase. Learning after 2 years of completion. I mean, we built this building. We are already in the building. We are working here. There are some learnings. In order to understand what is the difference between an assembly model, an as-plant model, you have to also understand what's an as-plant model, a digital twin for as-plant model, as-built model, and as-operated model. They're all different, right? So, and we are now questioning what is an as-operated digital twin. I will not go in detail because I am over time. So what is important here, there are two things that we learned. One is an assembly model is not necessarily an operation model. And in order to create a liable link from the operating building to the model, you need to have also the sensors, the data collecting points in the building. And that's kind of the most important thing if you want to create a data sensor data infrastructure, so that you can get live data and you can compare this the state of the building with the planned state of the building, and you can always compare, or the build state of the building, and you can always update it. And sometimes you have to transform your information for a CFM or a operation management system. And if you, from the beginning on, didn't thought about it, you will have a big problem once you build a building that your building is not an operation model, so that you have to apply a digital retrofit approach. What is a digital retrofit? Is like you start to reinform the build model based on the other logical information, so that actually operation system can understand what you mean. I can give you one example. In a typical Revit model, an object will not know in which room it belongs to. From the construction point of view, you don't have to. But from operation point of view, you have to specify this kind of information. And that's why you have to feed all these elements with this kind of information later on. And this was for us a bit challenging. So we tried, we know how to do it. We did some testings, but then we give up because it was not paying off anymore. But it was not also the main goal of this project. So what was the lessons learned? Assembly, a model, a digital twin is not necessarily the operational model. Facility management should be involved the same as the stakeholders. Like if I involve the installator company in the decision making and the decision of the model construction, also the facility manager should be involved in that stage, because only then it pays off. Only then it makes sense. And we learned that data can inform data. If you have a structural model, it doesn't matter if that particular information is not in the model. With a structural model, you can reinform it, and there's no limit of that. The question is always at which point it pays off. Okay, what we learned from this project is we work together over all phases. Like if I always said producer, installator, specialist, engineers, they have to come all together around one model if you really want to make a continuously non-breaked digital approach. So, and that's why it's a challenge, because that's not typical in Swiss construction industry. I mean, that's why you have to a bit avoid most of the cultural barriers here, and you have to really get involved as much as people you can in really early stage at the time being when the model was established. So coming together is the beginning, keeping together is the progress, and working together is the success. That's what Henry Ford said, and that's, I think, we tried to manage, I mean, partially even in this project. So that I would say. And benefits for a fully digital approach is, well, system integration allows you to optimize your engineering. New installation methods can save a lot of construction time. Prefabrication reduce waste and logistic complexity. If you manage to control the production, you can manage to also optimize the construction side. Not spending as much as time on creating drawings, but instead of them focusing on the model, which I mean data structural, the information model, it's really the biggest game changer here. Product-oriented design is necessarily for having an assembly model to have a better material output and cost estimation. And if a model is generated data-driven, I would say you can easily produce and assembly it. And potentially, for operation, it was also necessary, but you have to also know the processes related to the operation. Right. Before I conclude, the Future 3 project is now in the evaluation for the Creative Design Award from Structural Engineers. So if you can give a click to the link and can vote the Future 3 in this international competition, really appreciate it. It's a really good project. And if you want to get further information about this project, there are a lot of videos. You have to just Google in YouTube or in Google Basler Hofmann, Esslingen project, and you will see different videos about these different technologies that I presented you. So that's it. Thanks a lot. And I know we have over time, but if you have one or two urgent questions, I'm more than happy to answer them.
Thank you very much, Gianluca, and I guess we can give our emoji clap now for the talk. With that, thank you again, Gianluca, for the great presentation.